Okay, so in my presentation I would like to summarize a research program which we have been dealing with for the last 3 years. This program is devoted to two kinds of spaces. First type of spaces are four-dimensional neutral spaces, which are spaces equipped with the smooth metric of the neutral signature. And especially I would like to focus today on so-called Para-Kahler Einstein and para-Hermite spaces. And the second type of spaces are more general four-dimensional complex spaces, which are spaces equipped with the holomorphic metric, and especially I would like to focus on so-called hyperheavenly spaces. So the first question is, why real neutral spaces? Someone can say that we believe that structure of space-time is completely different. Signature of the metric is Lorentzian, so such neutral spaces cannot be directly used in general theory of relativity. It's true, of course, but I believe that such real neutral spaces also are quite important because they found their place in other areas of theoretical physics, for example, in integrable systems, because they admit anti-self-dual conformal structures, and at the same time, they do not need to be conformally flat. Then they appeared in the problem of two bodies which roll on each other without slipping or twisting. And finally, quite recently, an interesting relation between Para-Kahler Einstein spaces and so-called non-integrable crystal distributions has been found. And it was exactly this problem which motivates us to formulate the following research program. Namely, to find examples of all Petrov-Penrose types of Para-Kahler Einstein and para-Hermite Einstein spaces. This goal has been partially achieved. The first step has been made in 2017. In this paper, we have found examples of para-Hermite Einstein spaces of the types 2, T, and 3. And examples of all Para-Kahler Einstein spaces of which are algebraically degenerate. But these were only examples. There were no general metrics. There were some gaps. For example, we weren't able to find any examples of the algebraically general Para-Kahler or para-Hermite space, and we wasn't able to find any example of type N para-Hermite Einstein space. Quite great progress has been made in these two papers, in which we have found all algebraically degenerate Para-Kahler Einstein spaces which are equipped with so-called non-expanding and expanding congruences of nullity. Now, of course, I will explain later what does it mean that a space admits congruence of self-dual and self-dual elastics. And quite recently, we included type D into considerations, and we have found the first example of type N para-Hermite Einstein spaces. Okay, the second question, why complex spaces? Four-dimensional complex spaces can be considered as some generic spaces for all four-dimensional real manifolds, in the sense that such real manifolds are hidden inside such four-dimensional complex space. And the main idea of so-called Penrose-Prevatsky program was to find techniques of obtaining real four-dimensional spaces from complex ones. Unfortunately, this program failed in the general theory of relativity, because to extract such a Lorentzian manifold from complex ones is a very hard problem. However, it is very easy to obtain real neutral slice from such a complex metric. The second reason is, in fact, are spaces which are called hyperheavenly spaces, which are a very general family of these complex spaces. These are spaces for which self-dual part of the very tensor is algebraically general, and anti-self-dual part is algebraically special. And in such spaces, Einstein vacuum field equations with cosmological constant can be reduced to a single hyperheavenly equation. And if you realize that for all para-Kahler Einstein and para-Hermite Einstein spaces, anti-self-dual part of the weight tensor is of the type B, or self-dual one, but in what follows I will assume that this anti-self-dual part is of the type B, then the following procedure seems to be very reasonable. So first step is to find the solution of type D hyperheavenly space. Then take a real neutral slice of such space, and as a result we obtain metric which is para-Kahler Einstein or para-Hermite Einstein. Okay, two remarks. All considerations are local, all metrics are complex in the sense that coordinates are complex, functions are holomorphic. However, if we replace these complex coordinates by real ones and functions by real smooth ones, then automatically we obtain four-dimensional space of the equipped with the metric of the neutral signature. And my presentation consists of three parts. In the third part, I would like to present criteria which we use for sub-classification of such para-Hermite and para-Einstein spaces and para-Kahler spaces, and remind some definitions. And finally, I will present quite general metrics of para-Kahler Einstein spaces and examples of para-Hermite Einstein spaces. Okay, so maybe we should start from well-known Petrov-Benov classification, which in my opinion is probably the most important criterion of classification in general theory of relativity. And I believe this criterion is most transparent if you consider it in the spinorial formalism. So instead of weight tensor, we consider a spinorial image of the self-dual part of the weight tensor. It is 4-index spinor, totally symmetric in all indexes. So according to Perlmutt's theorem, can be decomposed into the product of 4, in general different, one-index undotted spinors, which are called undotted Perlmutt spinors. And in general, these spinors are different, but there is a possibility that, for example, we deal with a double Perlmutt spinor, or triple, or quadruple, or with two pairs of two different double Perlmutt spinors. And this way we arrive at this famous Petrov-Benov classification. In complex case, there are 6 different types. In real neutral case, the situation is a little more complicated. And I do not want to talk about details here, but in such a real neutral case, there are 10 different types of Petrov-Benov, 10 different Petrov-Benov types. The second criterion is based on the properties of the very interesting geometrical structures which are called congruences or foliation of nullity. And in this case, also, spinorial approach is, in my opinion, better than classical formalism. So we consider as a starting point two-dimensional self-dual distribution D spanned by the following vectors. And it is integrable in the Frobenius sense if spinor M satisfies the following set of two equations. These equations, we call these equations self-dual analytic equations. And if you get integrable distribution, then you get integral manifolds, which are two-dimensional totally null surfaces that are called null strings. And family of such surfaces constitute a structure which is called a congruence of foliation of self-dual null strings. And of course, the similar considerations can be repeated in anti-self-dual case, but definitions are analogous. Now, this set of equations can be written in the equivalent form, in which we've got a new object, this one-index dotted spinor field, which is called expansion of the congruence. And here appears a problem, because in general theory of relativity, if we are talking about the expansion of the congruence, then usually we are talking about the expansion of congruence of null geodesics. This concept is quite well known in general theory of relativity. And such type of expansion of congruence of null geodesics, also will appear in my presentation very soon. But this concept of expansion of a family of two-dimensional surfaces is completely different. So what does it mean that family of two-dimensional surfaces is expanding or non-expanding? Well, congruence is non-expanding if distribution is parallelly propagated. In other words, spinor which generates this congruence is recurrent. So geometrically, if you consider a vector x, which is tangent at a certain point to the certain leaf of this foliation, of this congruence, and then we consider its parallel displacement along the arbitrary vector field B, and we find that this new vector is, in new point, is still tangent to new leaf of this foliation, it exactly means that distribution is parallelly propagated. And in this case, we say that such congruence is non-expanding. Such spaces appeared for the first time, I remember well, in the 50s, in the paper of Walker, and mathematicians called such spaces Walker spaces. Okay, so with congruences of null strings, a very interesting theorem, which is complex counterpart of the Goldberg-Sachs theorem, is related. It is so-called generalized or complex Goldberg-Sachs theorem. It says that in complex Einstein spaces, following two statements are equivalent. Space admits a congruence of null strings, and it is generated by the spinor M. And exactly the same spinor is a multiple kernel spinor. So self-dual spinor is algebraically degenerate. And from this complex generalized Goldberg-Sachs theorem, which on this relation between congruence of null strings and algebraic degeneration of the self-dual part of the veil tensor, we can arrive at the definition of hyperheavenly spaces, which are four-dimensional complex manifolds equipped with the holomorphic metric, which satisfies Einstein field equations with cosmological constant, and for which self-dual or anti-self-dual part of the veil tensor is algebraically degenerate. So in what follows, I will assume that anti-self-dual part is algebraically degenerate, but switching orientation, we can consider a case in which self-dual part is algebraically degenerate. The metric of any hyperheavenly space can be presented in this form. Q, P, X, and Y are local coordinates, and I will refer to these coordinates as to the hyperheavenly coordinates. This metric depends on one function of four variables, which is called T function, and the set of 10 Einstein field equations with cosmological constant in vacuum with cosmological constant can be reduced to the following single equation, which is called hyperheavenly equation. So any solution of this equation gives us a metric which is hyperheavenly. Okay, another important conclusion from the complex Goldberg-Sachs theorem is as follows. If a space admits two different congruences of self-dual and anti-self-dual null strings, then self-dual and anti-self-dual veil spinor is of the Petrov Penrose type D. And two different congruences of anti-self-dual null strings implies and is implied by the fact that space is of the type D. Here I am talking about the Einstein spaces. So it is true in Einstein spaces. And now we can define para-Hermite and para-Kahler spaces as real manifolds equipped with the smooth metric of the neutral signature, such that following a condition is satisfied. A space admits two different expanding in the case of para-Hermite and non-expanding in the case of para-Kahler congruences of the null strings of the same duality. And usually, but many papers devoted to this para-Hermite and para-Kahler spaces, the definition is at the first glance completely different, because such spaces are defined with help of the integrable para-complex structure, which is metric compatible. But such a definition is equivalent to this one, and this one is much better for the purposes of my presentation, so I prefer this definition. Okay, so it was the second criterion. So what about if a space admits two congruences of null strings of the different duality? They intersect, and intersection constitutes the congruence of null duality. So if we deal with such a space which is equipped with two congruences of different duality, then we can define complex expansion and complex twist by exactly the same formula as in the Lorentzian case. And we can use these scalars for sub-classification of such spaces. And obviously there are four possibilities for which I use the following symbols. In para-Kahler Einstein, para-Hermite Einstein spaces, only congruences which are expanding and twisting, or non-expanding and non-twisting can appear. Okay, so now we need a unique symbol in which we gather all this information. In general theory of relativity, usually it is enough to say that the space is the type N, or the type D, because self-dual part of the Veil tensor and anti-self-dual part are complex conjugated, so if one of them is of the type N, then the second also must be of the type N. In complex spaces and in real neutral spaces, it is not true anymore, because these two parts of Veil tensor are independent. So usually we use such a symbol, in which information about the Petrov-Penrose type for the self-dual and anti-self-dual parts of Veil tensor are listed separately. Moreover, if space admits congruences of null strings, then we add some superscripts. A number of the superscripts tell us about the number of different congruences of self-dual and anti-self-dual null strings. And they can be equal n or e, n like expanding, p like, n like non-expanding, p like expanding. Moreover, in this square bracket we list properties of intersection of such congruences. So maybe a few examples. So hyperheavenly spaces in this formalism can be written like here. Self-dual part is algebraically arbitrary. Anti-self-dual part is algebraically degenerate. It can be equipped with a non-expanding or non-expanding congruence of null strings. Para-Kahler Einstein spaces, the para-Hermite Einstein spaces, there are the following types. Anti-self-dual part is of the type D, and the difference lies in the properties of congruences. Both of them must be non-expanding, or both of them must be expanding. So-called two-sided Walker spaces are spaces for which we've got two different non-expanding congruences of different duality. Then so-called sesqui-Walker spaces, which are generalizations of the two-sided Walker spaces, can be written in this with help of the symbol like here. We've got here two different families of such sesqui-Walker spaces. Okay, this example is maybe not so important. So, in the second part of my presentation, I would like to present algebraically degenerate para-Kahler Einstein space, matrix of such spaces. So, very quickly we can find that para-Kahler Einstein spaces can be divided in four different classes. And suddenly this particular slide was the last slide of my presentation, of my talk, which I gave 1 year ago during the previous POTOR conference. So 1 year ago I said that I hope that today here in Krakow I will be able to present examples of this algebraic general para-Kahler Einstein spaces. But unfortunately this problem is much more complicated than I suppose it is. So, still, examples of such spaces are known. On the other hand, all algebraically special para-Kahler spaces, which can be divided in such three classes, are all known in all the genera. Okay, so the simplest class can be presented in the form of the following diagram. So we've got these straight lines symbolize two different congruences of anti-self-dual null strings, which are, and because they are straight, they are non-expanding. So we've got two different such congruences which are anti-self-dual. It's a common property of all para-Kahler Einstein spaces. And we've got one self-dual congruence which is also non-expanding. Intersections are necessarily linguistic and non-expanding. And the only possible type is of such spaces is type 2 cross B. Metric of such type can be written like here. We've got here two functions of the variables. The only possible degeneration of this type is the type D cross D, so another self-dual congruence appears. We've got four different intersections and all of them are non-twisting and non-expanding. This metric is very simple, it depends only on cosmological constant and it admits 6 unit vectors. The second class is more complicated. We've got here expanding congruence of self-dual null strings, still two non-expanding congruences of anti-self-dual null strings. These wavy lines symbolize that this is expanding. But now, first intersection is non-twisting and expanding, the second is twisting and expanding. In this case, we've got three different Petrov-Penrose types, 2, 3, and n. In general, we've got three functions of two variables in this metric, and of course a cosmological this case also, a reduction to the type D cross D is possible, but in this case there is another congruence of self-dual Einstein which is expanding, and there are 4 intersections, but 2 of them are non-twisting and non-expanding, and 2 of them are twisting and expanding. And in this case, we find the metric in the following form. Key function depends on cosmological constant and 2 other constants. And this metric depends, is equipped with 4 different Killing vectors. The last class is the most complicated. In this case, self-dual congruence is still expanding, but intersections are twisting and expanding. Both are twisting and expanding. And this metric is the most complicated. It depends on 4 functions of 2 variables. For the type N, there is a small problem because only one of these functions must vanish, but 3 others are constrained by this equation. And this equation in hyperheavenly coordinates cannot be directly solved, explicitly solved, but if we change slightly coordinates, then we can arrive at the explicit form of the metric, which is quite advanced, but explicit. And also, in this case, reduction to the type D is possible. We've got the following diagram for which all intersections are twisting and expanding. And in this case, the metric can be right in standard hyperheavenly form with key function given by the following for polynomial. Except cosmological constant, we've got 3 other constants. And this metric depends on these 2 Killing vectors. Okay, so maybe very quickly I will present also some examples of para-Hermite Einstein space. A few years later we were able to find, well, first of all there are much more possible classes of such spaces. According to my best knowledge, none of them can be, is completely solved, but I believe that this class 3, which is equipped with non-expanding congruence of self-dual Einsteins, can be solved completely. I'm not sure of course, but I feel that they can be solved. As examples, these examples are of course much more complicated than corresponding Para-Kahler metrics. So for example, here we've got an example of para-Hermite Einstein space of the type 2 cross B. Even more scarier example of the Einstein para-Hermite space of the type 3 cross B. And as I mentioned earlier, in a paper published in 2017, there was no examples of the type N. However, recently we have found quite a simple example of the type N cross B in a para-Hermite space. This is the only known example of such space, and at the same time, it is a general solution of such type of para-Hermite Einstein spaces. So N cross B. A single self-dual congruence, non-expanding, 2 expanding congruences, both intersections are twisting and expanding. It depends only on one function of one variable and a single constant. Okay, so as a short summary of my presentation, I want to point 3 directions of possible further investigation. So the most obvious question is about this algebraically general para-Kahler Einstein spaces. Still there are no examples, and I still believe that such examples can be explicitly presented. The second question concerns para-Hermite Einstein spaces. Can such algebraic degenerate spaces can be solved explicitly? I believe that some of classes can. And the last direction is probably the most promising. It is based on the old idea investigated in paper by Krakow, Chudecki, and Formański, in which they investigated a superposition of 2 type N solutions of heavenly spaces. So type N cross nothing spaces, 2 such solutions from which they created a single solution of the type N cross N, and they tried to check if such an approach can give a twisting and vacuum type N problem, which, as you probably know, or is one of the most famous unsolved problems in general theory of relativity. So our idea idea is to take Para-Kahler Einstein space, para-Kahler, not Para-Kahler Einstein, but Para-Kahler spaces. Then obtain from them self-dual spaces, which can be quite easily done. Then consider superposition of such self-dual and anti-self-dual metrics, and check if we can obtain that way Lorentzian type n cross n metric. I'm not sure if it is possible, but I believe it is worth to check. And this is everything I wanted to say, so thank you very much.
Thank you very much. Now there is time for questions.
Is the motivation for studying these spaces purely mathematical, or could there be some physical relevance? Higher dimension, for example.
If by physics you understand only general theory of relativity, no, it's purely mathematical. But such neutral spaces also can be used in some physical problems, like mentioned in the introduction, problem of two bodies which are on each other without physical twisting, or for example, geometry of so-called 2-3-5 distribution, its relation to non-behavioral twist of distributions. So they can, but not in general theory of relativity, unfortunately. Or, like, but maybe they could be used in general theory of relativity, but I'm not sure if this idea leads to some useful conclusions.
When you spoke about null strings, you was meaning geodesic formations of null by vectors, or really surfaces which are emerging from shear action for null strings?
Could you repeat the question?
What was your actual meaning of the using the term null strings? It was just geodesic foliations of null by vectors, or it was surfaces fulfilling the equations of motion derived from the shear action for null strings?
I mean that foliation of null strings is a family of two-dimensional surfaces which are totally null and they are totally geodesic. So I guess that the first meaning.
Thank you.
Okay, I have a related question to this. Exactly, what do you mean by these null strings? Because in fact, you know, it's not in the context of the string theory what you think. But in fact, they are related because the null string can be considered a collection of photons, okay, which expand in space. So in fact, in string theory, you have the string tension parameter, which is in front of the action. You take this string tension parameter for the null strings to be equal to be approaching zero, and it's called tensionless string. Okay, and in fact, what you obtain, we have derived such solution, is a collection of photons, which is in fact subject to some constraints. And you can have, for example, them on a photon sphere. You can have a string which changes the size and cycling from one north pole to the south pole. So you mean that? I mean, it's a physical interpretation of all this. Yeah. So have you considered this in the context of string theory?
No, absolutely not.
Because I mean, there are two communities, you know, string, when they consider the things like this, and conventionalist strings. Here they are called null strings involved.
And this null string is a name which was created by Pebański and his team, so I keep this maybe old-fashioned name.
Tensionless string, I think, in string theory.
And no, it is not. These null strings just don't exist in Lorentzian spacetimes.
Yes,
I mean, it's a fairly, people call them alpha surfaces or beta surfaces. So null strings.
Okay, so it's not. Okay, you say that.
Signature of the metric is neutral in this case.
Okay.
And we have 5 remember well, in string theory, there are much more dimensions, but one of the signature is plus and some minuses, yes, and no plus plus.
Okay.
So it's probably not.
Discuss this. Anyway, okay, are there more questions?